So recording now. Okay. I did go back and make a video for those of you who caught that. So after class, I ran through the lecture again and I sent it. So if you still want to get that, you got it. If you just recently joined, go ahead and send me an email. I do see some of you right now, but I just put away my attendance. And again, once I put it away, I don't want to get it back out. Okay, so let's go back to sharing the screen. Okay, so I got one more question to do, maybe from section 2, and then go on to section 3, which is a pretty big section. Okay, so we are over here somewhere. Okay, so one more problem from the mean value theorem, and then section 3 is a biggie. It's on curve sketching. 4.3 and 4.5 are primarily curve sketching. Okay, so they give us a function, graph it. Okay, from the graphs we can determine maximum, minimum values. Okay, and other things that I haven't talked about yet, but we'll see. Okay, so 4.3 is mostly curve sketching. 4.5 is mostly curve sketching also. Let me go back and finish up something from 4.2 and get that out of the way. So 4.2 was the mean value theorem. Okay, and I was almost done. I was going to show you 17. So a quick reminder of where we were for the mean value theorem. Okay, so just give you the highlights again. Okay, Rowe's theorem, page 287, 3 hypotheses. Continuous on a closed interval, differentiable on an open interval, same height at the 2 endpoints, f of a equals f of b. Then there is a number c between a and b such that f prime of c is 0. Mean value theorem, we don't have the third restriction. Just continuous on a closed interval, differentiable on an open interval. Okay. Then there's a number c between a and b such that f prime of c is f of b minus f of a divided by b minus a. And again, I mentioned that Rowe's theorem and mean value theorem are really the same, because if you take the mean value theorem, if you kind of tilt it on its side, it kind of looks like Rowe's theorem, right? And the same thing for that graph. If you kind of turn your book, it looks like, okay, it's horizontal, and those red ones are horizontal. Okay. Okay, so I just wanted to show you number 17 and then go on to new stuff. Okay, f of x is x minus 3 to the negative 2 power, which is the same thing as 1 over x minus 3 squared. Okay, and it says, show that there's no value of c between 1 and 4 such that f of 4 minus f of 1 equals f prime of c 4 minus 1. In other words, it's not true that the slope of the line joining the 2 endpoints can be attained. Okay, so how do you do that? Okay, so first let's find the slope of the line joining 2 endpoints. They told us to go from 1 to 4. Okay, so what do you get when you plug in 1? 1 over negative 2 squared is 4, so 1 comma 1/4. And when you plug in 4, 4 minus 3 is 1, so 4, 1. Okay, so find the slope. Y2 minus y1 divided by x2 minus x1. 1 minus 1/4 divided by 4 minus 1. 3/4 divided by 3, okay, which comes out to be 1/4. Okay, I think I showed you this trick before. You can slide that 4 down with the 3. It becomes 3 over 12, which is 1/4. But what's the derivative of this thing? Derivative x minus 3 to negative 2. Well, it's negative 2. It's negative 2x minus 3 to the negative 3rd power, which I can choose to write like this. Okay, set it equal to 1/4. Cross multiply. X minus 3 cubed is equal to negative 8. Take the cube root. X minus 3 is equal to negative 2. Add 3. X equals 1, which is not inside the interval. Okay, the theorem says it has to be strictly inside the interval from 1 to 4, and this is an endpoint. Okay, and it says, why does this not contradict the mean value theorem? Because the function is not continuous at x equals 3, right? The function had to be continuous and differentiable everywhere between 1 and 4. You can see x equals 3 is not allowed, right? So that does not contradict the mean value theorem because the function is not continuous everywhere. Okay. Okay, so that's it for section 2. I'm done with the mean value theorem, and I'm ready to start section 3, which is quite a big section now. Okay, so we're beginning curve sketching. So 4.3, 4.5, a lot of curve sketching. Okay. So 4.3, how derivatives affect the shape of a graph. It's on page 293. And there's a lot of theorems. Okay, and again, it's because of the COVID crisis and all that, I will let you put all this stuff on your cheat sheet. But again, if we were meeting face to face, I'd make you guys memorize it. Okay, so let's take a look at this graph. Figure 1 goes like this. Okay, and our frame of reference is always moving from left to right. We're almost never going to go right to left. We're always going left to right. So if I go from left to right, A to B, okay, pretend it's a ride, like a roller coaster ride. Right here, I would say the function's increasing, right? It's going up. Right here, the slope is 0, relative maximum. Then from B to C, I would say the graph is decreasing. The roller coaster is going down, definitely. Slope of 0 at the minimum, and then increasing, okay? I don't know if you can see it. They've got these red tangent lines, right? Slope of the tangent line, tangent. So increasing, decreasing, increasing, and so on. What does that tell me about the derivative? Okay, well, derivative means slope, right? We know slope means derivative, okay? What can you tell me about the slopes here? Well, they're positive. Therefore, it's increasing. Slope negative, decreasing. Slope positive, increasing. Slope of 0, slope of 0. Okay, so that leads us to this. Again, you can put it on your cheat sheet, but you probably don't have to. You ought to really memorize it, but it's not really that hard if you think of slope. If f prime of x is greater than 0 on an interval, interpretation, positive slope. Function is increasing. F prime of x is less than 0, negative slope. F is decreasing, right? You already sort of knew that from algebra, right? When you were taking algebra, if you had a line like that, right? And say, oh, positive slope, function's increasing, going up. In algebra 1, if you had a negative slope, you say, oh yeah, it's going like that. The slope is negative, so the function's decreasing. This is the same thing, except in algebra 1, you didn't hear the word derivative, but now we know what derivative means. Okay, so positive derivative, increasing, negative derivative, decreasing, right? So these tells me where the function's increasing and decreasing. This is on page 293. All right, first derivative test, page 294. Again, you can put it on your cheat sheet, but you know, after a while, there's too much on your cheat sheet. You really should memorize it, but if you look at the picture, it's really not that hard. Okay, what they're showing you here on page 294 at the bottom, figure 3. They're showing you 4 cases where the slope is equal to 0. Tangent line is 0. Right here, right here, right here, and right here, okay? Slope is 0. Now, if you look at the graph, that looks like a local maximum, right? Local minimum. This one is neither. A good example of this would be the graph of y equals x cubed. Okay, slope is 0, but you can tell it's neither a maximum nor a minimum. And likewise over here, this would be like y equals negative x cubed. Slope is 0, but neither a maximum nor a minimum. Okay, so how can we categorize maxima and minima? If you hear me say maxima and minima, those are the plurals. One maximum, 2 maxima, 1 minimum, 2 minima. So anyway. All right, what makes this a local maximum? Well, if I move a little bit to the left, the function's increasing. If I move a little bit to the right, the function's decreasing. Right? Think of a roller coaster ride. Okay, I'm sure many of you have been on roller coasters, or if you've not been on roller coasters, you've seen one. Okay, you go up the roller coaster, then you go down. So you must have reached the maximum. Right? Now let's take a look at local minimum or relative minimum. Okay, slope is 0. A little bit to the left, the function's decreasing. A little bit to the right, function's increasing. The ride, the roller coaster ride, think you're on this roller coaster, right? You go down, then you swoosh and come back up, so you reach the minimum. Okay, now what if the roller coaster does this, which I've seen some roller coasters do? Okay, so here the slope is 0, but it's neither a maximum nor a minimum because you go up, and then the slope becomes 0, and then you go back up. Right, so that's neither a maximum nor a minimum. Likewise over here, if the roller coaster or even the slide, I've seen some slides, children's slides, they kind of go like that, right? You go down the slide, it goes like that, it levels off, and then it goes back down. Okay, so this is neither a maximum nor a minimum. You're decreasing. Of course, if you're going down a slide, you're decreasing, by gravity. You don't normally slide up. Okay, so you go down, reach a slope of 0, and then you go back down. All right, so we have a test. It's called the first derivative test. And of course, once we use the word first, that seems to imply there's a second derivative coming, and we'll get that shortly. Okay, so we have a first derivative test for maxima and minima. Okay, so you have a derivative of 0. We've seen that before. Derivative of 0 means a horizontal tangent line. Horizontal tangent, horizontal tangent, horizontal tangent. Slope is 0. Okay, suppose C is a critical number of a continuous function f. Okay, you have a critical number. What's critical number? Derivative is 0 or derivative is undefined. Okay, how can we tell if we have a local maximum? F prime changes from positive to negative. Then we have a local maximum, right? A little bit to the left, F prime is positive, increasing. A little bit to the right, F prime is negative, decreasing. That's what makes you have a maximum. Okay, B, how do you know if you have a minimum? F prime changes from negative to positive. Okay, so a little bit to the left, the function's going down. Function decreases. The slope is negative. You're going down the roller coaster. And then a little bit to the right, you're going up the roller coaster, right? So function is increasing. That means you have a minimum, right? And if you've been on a ride, and you don't have to think of roller coaster, think, you're driving a car. You go like that, and you go like that. So you reach a maximum. You go like that, you go down, then you go back up. So you reach the minimum. Okay, C, if F prime is positive, both to the left and the right of C, or they're both negative to the left and right of C, then F is neither a local maximum nor minimum. Okay, so that means if you go up and then you go back up, that's not counted as a maximum or minimum, right? And yeah, I've seen rides do that, or you go up, you reach the intersection, you level off, right? And then you go back up again. Well, that's not counted as a maximum nor a minimum. And likewise here, on a roller coaster or you're driving, right? You go down and then you level off, maybe at an intersection, and then you go back down. So this can't be counted as a maximum nor minimum because there are points that are higher and there are points that are lower. Okay, so that's the first derivative test. All right. Okay, so as you might guess, since we talked about first derivative, we're going to talk about second derivative. What does f double prime say about a function? Okay, so new vocabulary. Unless you've had calculus background, you've never heard of this before. Page 296. Concave upward, concave downward. I will normally just say concave up and concave down. Okay, so I will just say concave up, concave down. Okay, save on a syllable, right? Instead of concave upward, I'll normally just say concave up, concave down. So what's this concave up, concave down stuff? Okay, very crudely, concave up, the graph is curving like a U, U-shaped. Concave down is upside down U-shaped. Okay, so this is curving like a U, that's considered concave up or concave upward. Okay, this is curving like an upside down U, we're going to call that concave down. Okay, easy way to remember is U is up, right? The letter U is concave up. So take a look at this picture that they have right here, this figure. And yes, notice the author has the abbreviations, and I'll do this abbreviation also. CU and CD, because it takes too long to keep writing CONCAVEUPWARD and CONCAVEDOWNWARD. Nobody wants to do that, right? So concave up, CU, concave down, CD. Okay, so please follow what's happening here. Upside down U, U-shaped, upside down U-shape, 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 upside down U-shape for concave down, concave up, and so on. Okay? So concavity, we'll say a fancy word, concavity, talks about which way is it curving? Is it curving like a U-shape or an upside down U-shape? Okay? So concave down, concave up, concave down, concave up, concave up, concave down. Okay? I'm almost never going to say the word upward, downward. Okay. All right. Some characteristics of concave up. You don't have to write this down if you don't want to. I won't test you on it. But if you notice the tangent lines for concave up, the tangent lines all seem to be below the curve. How about concave down? It looks like the tangent lines are above the curve. So you could use that as a criterion, I suppose, for concave up and concave down. Are the tangent lines above or below the curve? All right. Now, there's a second derivative test that controls concavity. So the second derivative is for concavity, concave up, concave down. Okay. Let's look at the slope over here. Okay. If I consider the slopes, see the red tangent lines? It goes like that, and like that, and like that. So the slopes are increasing. Let's look at the concave down. Go like that, and like that, and like that. Slopes are decreasing. Okay, so concave up, the slopes are increasing. Concave down, slopes are decreasing. Okay, I can hear somebody's background. Can you please mute yourselves? Everybody please mute yourselves. Doing some background there. Okay, so concave up, slopes are increasing. But we already said, okay, can somebody please mute yourselves? Yeah, I'm hearing some background. Okay, if a function is increasing, then its derivative is greater than 0. If a function is decreasing, derivative is less than 0. Okay. Well, f prime is a function. Okay. If you take a derivative of a function, you get a function back. Okay. So slope increasing means f prime is increasing, which means the derivative of f prime is positive. What's the derivative of f prime? That's f double prime. Okay. And likewise, the slope is decreasing. Slope is decreasing. Okay. That means f prime is decreasing. So that means I need you to mute yourselves. Okay, sorry folks, I'm gonna have to, this is wasting some time unfortunately. But, okay, I think we're all muted. All right. So okay. So bottom line, you say, I have no idea what you were talking about. Okay. Here's the bottom line. Okay. Slope increasing means derivative is increasing, i.e. f prime is increasing. Rate of change of the derivative. That's the second derivative. Okay. So what do you need to know? F double prime greater than 0 means concave up. F double prime less than 0 means concave down. Okay, if you didn't understand my explanation over here, don't worry about it. This is the result of it. Some of you maybe got it, but anyway. Okay, and again, you were supposed to have this memorized, but since I'm letting you have a cheat sheet, go ahead and put it in a cheat sheet. So double prime greater than 0, concave up. Double prime less than 0, concave down. So the first derivative controls increasing, decreasing horizontal tangents. Second derivative controls concavity, concave up, concave down. Okay, now, page 297, inflection point. Sometimes we say point of inflection. What is inflection point? Okay, the function is continuous. The curve changes from concave up to concave down, or vice versa, from concave down to concave up. An inflection point is a change in concavity. Okay, give you some examples here. Okay. Point B is an inflection point. It switches from concave down to concave up. C is an inflection point. It switches from concave up to concave down. Okay, so those are inflection points. Now, this point right here is not an inflection point. It goes from concave up to still being concave up. So by definition, that's not an inflection point. This point here is an inflection point, point P, concave up, concave down. So whenever there's a change in concavity, that's called an inflection point. All right, inflection point. Now you say, how do I know if I have an inflection point? Okay, well, let's think about it. I didn't cover all the cases here. I had double prime greater than 0, concave up. F double prime less than 0, concave down. What's left out here? How about F double prime equals 0? And there's actually one more case where F double prime is undefined, but we almost never have that. Okay, for the homework problems that we have, for all practical purpose, F double prime equals 0 is a candidate for an inflection point. It doesn't guarantee that it's an inflection point. Okay, so F double prime equals 0, you might have an inflection point. Okay, you'd say, well, how can you tell for sure if it's an inflection point? Then you have to check the concavity on each side. Okay, so you will look to the left and to the right. So let's say on the left side, yeah, let's say over here. Suppose you have F double prime equals 0. Okay, on the left side, concave down, right side, concave up. That makes this an inflection point. Or C, okay, double prime equals 0. Okay, left side, concave up, right side, concave down. It's an inflection point. But let's pretend you have F double prime equals 0, but on both the left and right sides, it's concave up. Then it's not considered an inflection point. Likewise, if on both sides you have a concave down situation, then again, you no longer have an inflection point. Okay, so I know there's a lot of stuff going on here, okay, and I'll have to do some problems to show you what's going on now. Okay. Now, as if that wasn't enough, there's a little more. You have a second derivative test for maximum and minimum values. Okay, now that does not nullify everything we said here. Okay, so everything here is still correct. Okay, but there's another way you can tell if you have a max or min using the second derivative. Okay, let's look here. This is a maximum, right? Okay, does that look like concave up or concave down based on what we said? Concave down, right? Let's look at a minimum. Concave up, U shape. So more stuff. And again, if you want to put this on your cheat sheet, you may. Suppose F double prime is continuous near C. Okay, these two say slope is 0. Okay, so you might have a maximum. Okay, second derivative greater than 0. Let's see, second derivative greater than 0, concave up. Minimum, like that. Second derivative less than 0, concave down. You have a maximum. Okay, so here's such an example, like this. Concave down, second derivative less than 0, maximum. Okay, and by the way, here's another example of an inflection point. Here's an inflection point. Here's an inflection point. Looks like concave up, switches to concave down, switches to concave up. Okay. All right, so there's a lot of stuff here, as you can tell. And frankly, there's only one way to get used to this is to do a bunch of homework problems with it. Okay, do some homework problems with it. You kind of get the hang of it and go from there. Okay, so we're going to be sketching graphs like this. Okay, here's some things going on. Here's y equals whatever, but this is an inflection point. Okay, concave up, concave down, switches to concave up. So here's another inflection point. And the rest of the time looks like it's concave up. That looks like a relative minimum. In fact, that looks like an absolute minimum. Okay, so given a graph, this one looks like what? X to the fourth minus 4x cubed. We can analyze the whole works. Where is there a maximum, minimum? Increasing, decreasing, concave up, concave down, inflection points, all of that stuff. All right, so let's get our feet wet and try some of these problems. Okay, now 4.3, we have 1 and 2. So obviously you don't have the answer to 2 in the back of the book. I'll do 2, let you do 1. Okay, so here's question number 2. Given the graph, give the open intervals of which f is increasing. So where is f increasing? Okay, so between 0 and 1. And let's see, between, let's see, 1, 2, 3, 4 to 5, and then 5 to 7. Okay, so for 2a, I'm going to go 0, 0 to 1, union, where was it going to, 4 to, let's see, 1, 2, well, I'm sorry, forgot 3. 3 to 5, union 5 to 7. Okay, so that's where the function is increasing between 0 and 1. We only give the x values. When x goes from 0 to 1, now this would be decreasing. So from 3 to 5, and then 5 to 7. Okay, right at 5, you might say, how come I just go from 3 to 7? Right at 5, what's the slope? 0, right? So technically, it's not increasing here. It levels off just for a split second, and then it goes back up. So I have to write it like this. Okay, B, where is f decreasing? Where is it going down the roller coaster? You can see writing a right, it looks like this, right? Go up, level off, go up. So it's only decreasing between 1 and 3. 1 and 3. Okay, concave up, U shape. Let's see, right here, right? U shape. So that would be between, where is that? 2 and 4. And where else is it U shape? Right here. So what is that? 5 to 7? I wish they put the numbers there. 2, 3, 4, 5. 5 to 7. U shape. Concave downward, concave down, upside down U shape. So between 0 and 2, right? Upside down U. And let's see, right here, right? So where's here? 1, 2, 3, 4, 4 to 5. And then E, the coordinates of the points of inflection. Inflection point, where does it change concavity? So right here, right? So what is that as an ordered pair? 2, 2. And where's the next inflection point? Here and here, right? So where's here? 1, 2, 3, 4, 1, 2, 3, 4, 3. And where's that? 5, 4. Okay, and something you may notice, it looks like the same notation here, but these are different. These are ordered pairs, right? This is x, comma, y, and so are all these. These are all x's. These are all x1, x2, everything here, x1, x2, x1, x2. Okay, it's an open interval from one x value to another x value. These are points, x comma y. Okay, so that is that. Now I want to show you at least one curve sketch in the time we have left. We only have 15 minutes left. I'll give you the idea behind curve sketching. Okay, to give me this function, f of x equals blah, 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 or whatever. I'm going to try to do one of these at least. And let me see which one I was going to show you. Yeah, number 9. X cubed minus 3x squared minus 9x plus 4. Okay. Find the intervals where f is increasing or decreasing. Find local max and min. Find intervals of concavity, inflection point. So all of that just from this. Now, in pre-calc, how did you graph this? You probably just plotted a whole bunch of points, right? And that's pretty much it. And then say, how do you find the maximum and minimum? Maybe your pre-calc teacher said, wait until calculus. This is the period now, right? How can I find maxima and minima points on this? Okay, so let me show you how this works. So f of x equals x cubed minus 3x squared minus 9x plus 4. Okay, the usual thing you want to start off with is taking 2 derivatives. Okay, so start with 2 derivatives, and whenever you can factor. So first derivative, 3x squared minus 6x minus 9. Factor, take out a 3, x squared minus 2x minus 3. Factor this, 3 times x plus 1, x minus 3. Okay, find the second derivative, double prime, 6x minus 6. So there we go. All right, now, set f prime equal to 0. Right? And you were also supposed to say set f prime to be undefined, but this is not undefined. Okay, we're trying to find critical numbers. Why the critical numbers? They might be maxima or minima. So take the factored form, 3 times x plus 1, x minus 3 equals 0. That's easy. X equals -1 and positive 3. Plug in to find the y values. So f of -1, plug it back in here. F of positive 3. Okay, so plug in -1. -1 cubed, -1, minus 3 times -1 squared, that's -3. Then -9 times -1 is 9, plus 4. If you work that all out, it's 9. So I have -1 comma 9. Plug in 3. 3 times 3 squared, 27. Whoops. Right here, 3 cubed, 27. Minus 3 times 3 squared, 27. Minus 9 times 3, 27. How do you like that? 3 27s in a row. And then plus 4. So these cancel out, -23. Okay, so my ordered pairs are -1, 9, 3, comma, -23. I have horizontal tangents there. Okay, now we don't know the graph yet, but -1, comma, 9, horizontal tangent. 3, comma, -23, horizontal tangent. I've already given away the graph, but pretend you don't know that right now. All you know can't even cover it. All you have is that and that. So how do we know if we have a maximum or minimum? Okay, so I make a sign chart. Sign chart very similar to our sign charts before. Look at the derivative, 3 times x plus 1, x minus 3. Okay, and here's my derivative. So draw my number line, -1, 3. When I plug in -1, I get 0. Here's f prime. When I plug in 3, I get 0. So everywhere else, it isn't 0. If it isn't 0, it's going to be either positive or negative. So just determine positive or negative. So just like the sign charts before, pick something over here, and over here. So over here, -2. Here, 0. Here, 4. Okay, I only need a sign. Okay. 3 is always positive. So that plus, that represents the 3. Okay, now I'll plug in here. -2. -2 plus 1, negative. -2 minus 3, negative. So what's a positive times a negative times a negative? Positive. So I just put a little plus there. So this, before we said true or false, right? Now we're not saying true or false, we're saying positive or negative. Okay, 0. 3 is positive. 0 plus 1, positive. 0 minus 3, negative. Multiply them all together, negative. So notice we're not saying true or false, we're saying positive or negative. Okay, plug in 4. 3 is positive. 4 plus 1, positive. 4 minus 3, positive. They're all positive, positive. All right. So we are doing the first derivative. Okay. So show you back in the text. Here again, right? Page 293. First derivative, positive, greater than 0. F is increasing. First derivative, negative, decreasing. So increasing, decreasing, increasing. So these would be my abbreviations for increasing and decreasing. Okay, it's very suggestive. Okay, you can write the whole word increasing for increasing, and what? decreasing for decreasing. You don't want to do that. I don't want to do that. Just go like that: increasing, decreasing, increasing. Okay, now watch this. Around -1, slope of 0. Increasing, decreasing. In fact, you can almost just look at this. That means this is a max, right? From what we said, if you move a little bit to the left, you're going up the roller coaster, right? Then you go down the roller coaster. So that clinches that -1, 9 is a relative max. Okay. How about 3, -23? Slope is 0. A little bit to the left, decreasing. A little bit to the right, increasing. So if you're on this ride, if you're on a roller coaster, if you decrease and then you increase, you must have reached a minimum. You bottomed out. So that tells me that 3, -23 is a minimum. Okay, so that tells me the graph increases, decreases, increases. So I haven't done concavity yet, okay, but the graph goes up, slope is 0, then it goes down, slope is 0, and then it goes back up. Okay, so I'm done with the first derivative analysis. I've got maximum, minimum values, or maxima and minima, but I want to get concavity now. Okay, so that's where the second derivative comes in now. Okay, so this is called intervals of increase and decrease. Okay, so where is the function increasing? From -infinity to -1, and also from 3 to infinity. So f is increasing from -infinity to -1, union 3 to infinity. So up until -1, increasing, and also from 3 to infinity, it's increasing. So where is the function decreasing? Only between -1 and 3. And these are open intervals. Okay, mind you, again, these are not points like x comma y. This is x1, x2. They're both x coordinates. So the graph is decreasing only between -1 and 3. So this ride, this roller coaster goes down only between -1 and 3. And yes, we have -1, 9 as a relative max, and 3, -23 as a relative min. You can put loco, LOC. I prefer relative. Okay, so the slope was 0 here. Now we know it's a max. Now we know it's a min. Okay, now the second derivative analysis. Okay, you pretty much do the same stuff for the second derivative as you did for the first derivative. So back over here, we set f prime equal to 0, right? Now do the same thing with double prime. Set f double prime equal to 0. Okay, so where was my second derivative? 6x minus 6. Set that equal to 0. Let's see, where'd it go? Okay, 6x minus 6 equals 0. That's easy, x equals 1. It's going to be a point, so I need the y coordinate. So plug in 1 back to the beginning. Okay, 1 minus 3 minus 9 plus 4. 1 minus 3 minus 9 plus 4. Yeah, you can just barely see both of these. If you plug in 1, that's 1 minus 3 minus 9 plus 4. Comes out to be -7. Okay, 1, -7. Second derivative is 0. But is it an inflection point? Well, we do the same test. So you know how we did a sign chart for f prime? Do a sign chart for f double prime also. Okay, so all these problems, you have the same process pretty much. You do the same process. F double prime, 6x minus 6. When I plug in 1, I get 0. That means if I plug in anything else, I don't get 0. Now, this is easy enough that I don't really need to do a full sign chart. Okay, you can just plug in and tell. Okay, so plug in 0. 6 times 0 minus 6, negative. Plug in 2. 6 times 2, 12 minus 6, positive. Okay, negative, positive. Okay. Second derivative. Second derivative. Second derivative positive. Whoops, I didn't want that. Yes, we do have a minimum, but I wanted this side. Page 296. Second derivative positive, concave up. Second derivative negative, concave down. Okay, second derivative negative, concave down, CD. Second derivative positive, concave up. So this is or is not an inflection point. It is an inflection point because there was a change in concavity. Okay, but let's say this is CD and this is still CD, then this would not qualify as an inflection point. Okay, so intervals of concavity, just like you have intervals of increase and decrease, the function is concave down from -infinity to 1. Function is concave up from 1 to infinity. Is there a change in concavity? Yes, there is. So that means 1, -7 is indeed an inflection point. So I'm ready for the whole graph. Okay, so 1, -7. And by the way, you don't have to graph these that accurately. You know, say I didn't mark 1, 2, 3, 4, 5. So you don't want to do that. Some of these numbers get really, really big. You might end up with 2, 45 and 7, -23. You don't want to count -23, right? 1, 2, 3, 4. You don't feel like doing that. Just the relative positions. All right. So here we are. We have the whole graph analyzed. So intervals of increase and decrease, it goes up, down, up. Okay, so increasing up until -1, increasing to -1. And then it goes down between -1 and 3, and then the rest of the time it goes back up. Relative maximum, relative minimum. For concavity, concave down from -infinity to 1. So upside down U-shaped up until the inflection point, and then the rest of the time concave up. It switches to concave up, like so. Okay, and here is one example of an entire curve sketch. You can see some of these problems do get kind of lengthy, and I realize that. So here we go. Okay, a real side note, people who make roller coasters, this is always there. I'm not saying you have to do this the next time you ride in a roller coaster. Usually when you ride a roller coaster, all you want to do is, right, just have fun. You don't think about this. But people who design roller coasters behind the scenes, they always have to consider this, right? When is the graph increasing, right? Okay, when is the roller coaster increasing, decreasing? Concavity is there, right? Concave down is there, concave up, okay? And I don't know, for those of you who like roller coasters, at an inflection point, there's sort of a different sensation. Okay, once you go like that and you switch over, there's that different feeling of being thrown, or you feel like you're falling away from the roller coaster. That happens sometimes at inflection points. Okay, so there's a lot of good math, obviously. Well, there better be good math in the roller coaster. If there wasn't good math, it would break down. But there's a lot of good physics, obviously. But there's a lot of good math. Increasing, decreasing, maximum, minimum, the highest point on a roller coaster, lowest point on the roller coaster, right? Concavity is there, concave up, concave down. There's definitely there when you ride these roller coaster rides. Okay, so that was just one problem, and we're just about out of time. but for tomorrow, I'll do a lot more. So we'll analyze these graphs, right? So when is the graph increasing, decreasing, maximum, minimum, concave up, concave down, inflection points? We'll be doing a lot of that kind of stuff. Okay. All right. And we are out of time, folks. So I will stop that. Let me check to see if anybody had a quick question from the chat. I don't see that. There's obviously not time to do anything else. Okay. So we're done for today, folks. All right. So tomorrow I'll just do more of these and we'll continue on and see how far we go. All right. So that'll be it for today, folks. So have a good afternoon and we'll see you next time. Okay. Bye, everyone.